This conference will now be recorded.
Okay, good morning, everybody. Welcome to the OCP HPC subproject regular call. It's 11th of July 2023. And today on the agenda, we've got, and Callum's on, I'm glad to see, we're going to go, Callum's engineering team gave us some good feedback, which we're going to walk through today and discuss that. And also we had, I was a couple of weeks ago, I was at the OCP CMS Tech Summit where I gave a presentation on CXL enablement. And just to let you all know really about that and point you to the slides. But the focus of today is on the cool IT feedback. Just as we get started, in an introduction to new attendees. So Bijan, I know most people probably know you, but maybe on the basis I didn't introduce you on the last occasion, would you mind just giving a brief introduction of yourself?
Certainly. I'm Bijan Nourouzi. I'm the CTO here at OCP. I've been on board for almost getting close to a year in August. So you'll probably see my face more and more on this project. I've had a lot of things that I've been working on that we're kind of coming to conclusion, that we're finalizing. So I intend to spend a little bit more time here.
Okay, great. That's good. Great news. Thanks, Bijan. And who's just joined? Pradeep. Hi, Pradeep. Welcome aboard. Let me just capture you here. Okay, so let me just switch over to. So Callum, are you ready for this? Basically, I've got the model open, and so we can look at the model and we can go through your bullet points as appropriate. So, do you want to kick us off, Callum?
Sure. Yeah, and I have this pulled up too, Alan, so feel free to just show the CAD. So yeah, again, just to preface with, I know a lot of these questions are probably a little early because I know the design is still being fleshed out. So hopefully this will just be more for discussion points, I think, and things to consider as this is taken further. Yeah, maybe Alan, can you bring up the
yeah,
CAD?
so I wonder if I can tuck this in the corner here and actually bring the model up alongside it. I don't know if that will be good for everybody or not. Let me just shrink this down.
Perfect.
Okay, there you go. Hopefully that's readable.
Perfect. And can you show the module with the cooling module on this top side as well?
Yeah.
If not, that's okay.
Wrong one. This one here.
Yeah, perfect. So yeah, a lot of the feedback from my engineering team, it's pretty high level right now, and I think as we go further, we can probably get more on like the DFA kind of side of things, designing for manufacturing. So yeah, the first comment is just being regarding tolerance stackups. I think something like this, it'll be very important to do statistical tolerance stackup analyses on each important joint. So one of the major comments there is just the fact that there's important interfaces on both sides of this PCB. That's where you really have to be conscious of, like, normally you're trying to control for one datum, and if you have two important interfaces, like the top side contacting whatever main chip there is, and then the bottom side also needing to be pretty tight tolerances with connectors and things, what becomes very critical is how do you control for that tolerance stack up of just the PCB itself and connecting between those two. that top water chamber and the bottom. So that's normally a situation where you'd likely want to try to add some flexibility somehow. If you have a brazed connection there, that's where you might run into problems. But something to really focus.
Yeah, so on the stack up side of things, I can see a couple of areas. Like you particularly highlighted this top cooling chamber, and well, we've not actually shown the interface here. There will be a little water connection between this bottom plate and the top. But I was assuming that would be some sort of interface and would be some sort of just a rubber sealed water joint. Is that not viable? Whereas you're mentioning braze, are you thinking the two would actually be brazed together?
No, like brazing would make it quite hard from a tolerance perspective. Rubber, if it's a rubber seal joint, that becomes quite rigid as well, unless there is some sort of like a rubber flexible material, but normally like a rubber gasket seal, it's still a rigid joint screwed together. Whereas we likely need something to eat up that stack up. So normally, if you have the space, you'd maybe connect those passages with rubber tubing or something like that. Or in braze cases, what I've seen before is if you have the space, you can do stainless steel corrugated tubing. I haven't seen anything particular that would give you that full kind of seal around flexibility with like a rubber joint, but not to say that doesn't exist. It just, yeah.
Well, I was thinking like a rubber washer where you've got some compliance in the vertical direction. So as you bolt the two together, that you get compression there.
Yeah, the difficulty is, so when you have like a gasket like that, usually there's like a specific range you're trying to hit with compression, and you want it to stay within that. Versus we're asking for compliance in that vertical direction. The risk would be like if you have a compliant enough material, maybe you're losing a seal when you're going in a larger gap tolerance stack up. So not to say there's not material out there that exists like that. I just have not seen that in the industry.
I guess just thinking out loud. So initially we had the water coming into the top chamber, and if you remember, Patrick can bring it up. Here is the original one where it was just one piece where the water came into the main chamber and went up and down the walls, and we had just a pure wall cooling with the wedge locks. So so in this sense there wouldn't be anything to worry about in what you're talking about there, right? I guess the other thing that we did is these Stolberly connectors with 3mm pipes in the water flow. I remember back probably a year ago now, when Boyd were helping us out. We were talking about the flow we would need to cool these, and that was why we've got two of them to get enough flow across the processor to cool the 1 kilowatt or the total 1.4 kilowatts here. So again, just thinking out loud, the only idea I was, either we could, yeah, okay, no, I think that's a bad idea. So this would need to be two pieces. It would need to be separable because you need to mount the PCB between it. And so the only thinking that was coming to mind here was if with these two water connectors, we actually had one of them going into the top piece and the other going into the bottom piece. Mm-hmm. And so separate circuits, so to speak.
So just so I'm going to ask a couple of dumb questions. First time I've really looked at this. So is this a pressurized water design?
When you say pressurized, no, not particularly. There's a separate loop between multiple modules, It's not, at the moment, it's not a two-phase design, it's just a pure liquid design.
So just a water glycol mix, not a two-phase material.
Yeah, so it's water in and water out, treated obviously. And the idea here is that we would control the flow through every module, because every module will be burning a different amount of power, and the outlet of the water would always be in the region of 65 C, so that we're compliant to the energy reuse temperature requirements. And so,
okay, I'm sorry, go ahead. My fault.
yeah, so that's the idea. Is we would, so different modules burning different powers would have different flow rates through them. So we'd have back in the wall itself that connects these pipes, there would be some variable valves that would control the flow in and out of the module. But it would be a pumped flow. We have been talking about the possibility of thermosiphoning, but we're not sure if that would work yet. But so it would be pumped.
Oh, may I ask you a question? No, are the electronic device or server, whatever, that being cooled are being housed inside the panel?
Yeah. Sorry. So no, everything's housed in this module.
The module that in the gray color, right? That vertical.
No, these are the media modules. So these are E3.S as an example. These modules, there's 16 of them. And then under this lid here, the water chamber is where you'd have your main processor. So this is your 1 kilowatt GPU or CPU or FPGA or whatever, or switch. This can be a switch as well.
You know, and again, dumb questions, since I'm looking at this the first time. I think you're going with it, but you know, you're very close to being able to convert this into an immersion design.
So the idea is that immersion is you wouldn't flood all of this, because yeah, this
it's a very handy form factor for immersion. I was just looking at that going
well it is and it isn't, because we're looking at serviceability. So the idea is we're trying to directly liquid cool everything with no air. And these modules would be plugged into a physical wall in the data center. So your 19-inch racks are replaced by a wall.
right.
So these would be mounted vertically on the wall. You wouldn't put them in immersion because well, they'd be very shallow, and you need to. It's all about serviceability. We want a gantry robot to be able to service this as well. It would be entirely a closed data center with no human involvement, ideally. So I guess we could get right in the weeds. Bijan, maybe you and anyone else, we could have a separate call where I can bring you right up to speed on all the details, so you get the full view of how this maps. This is direct liquid cooled is the idea of this, rather than cold plate approach as opposed to immersion.
Yep.
I'm sorry, another dumb question. The module that you described, the currently hanging, you know, in gray color, are those yeah, correct. Are there water pipe running inside, or it's just a solid piece of cold plate?
No, so these are E3 modules. So if I just remove the lid of this one a minute.
Yes, sorry, I don't know what the E3 module.
So this is media modules, basically, like SSDs or CXL.mem. They'll have a controller or controllers at the bottom, like this one. And in this, this would be a copper lid, and we would conductively cool down to, and this is what we're thermally modeling at the moment, is we'd have some sort of thermal coupling here between the actual module itself and this copper plate, and this copper plate would have the water flowing up the vanes between the modules, and so you'd have water directly attached to these cold plates. So you would conductively cool that, and Ender, I don't think Ender's on the call, but he's currently firmly modeling that for us. We've got in fact, I've got another smaller model of just a single module being plugged in. So that's what we're investigating there. There are some suggestions that we'd actually put water into these E3Ss, but I think that complicates. We're trying to work with existing E3S technology rather than have to introduce water to them. So we're just investigating, because these are in a region of 25 watts, for which isn't too bad to cool, or 40 watts if we're going to take a double width E3 and shrink it down to a single width. But the 40 watt budget is what the air cooled double width ones take, if that makes sense.
Okay, so they are not currently, they are not submerged in the water, not
No.
immersion
So
type.
they're conductively cooled through these. The water's flowing through this copper chamber here, or this chamber here, and so the water is directly underneath the module in this, and this is the inlet one as well, the inlet water, so it's relatively cool, and that will be pulling the heat out of the module through the copper plate. And this lid potentially could have could be a vapor chamber type thing if we needed better conduction, but at the moment it's a solid piece of copper or aluminum if that is sufficient. Okay.
So the whole casing itself, they are just exposed to the air, or this whole thing gonna be submerged in the water?
No, this will be exposed. The other thing we're talking about is obviously that we don't want the heat to escape too fast into the air. The air is going to end up being the same temperature of the water eventually. So we are talking about having insulation materials around these, where so you don't have much of the heat escape into the air, and you need only minimal air cooling. Or the data center itself could sit at 65 degrees C, for instance, if no one's going in there. So that's the concept. Is we put insulation around these chambers to keep all of the heat transfer into the water, so that we've got everything. You've got maximal capture for energy reuse by getting the water to 65 C. That's the principle of the idea. So what we've done is we've looked at this completely radically from a ground up. How would you architect a data center around sustainability, energy recovery, power loss minimization, and signal integrity? So you're crunching everything, just like we've been shrinking silicon forever, and we're introducing chiplets. We're sucking the server into a package. This is saying, well, let's now do the same sort of approach to the system level. But we've got to be far more radical than other projects like standard servers, or what I guess what the modular platform is trying to do, which is a bit more traditional looking. And if we look at direct water cooled solutions today, the water cabling is a nightmare in the server. So what we're doing is we're saying, let's make the water management the first primary thing to manage, and we'll make the electrical the cabling piece, rather than at the moment we've got water cabling and we've got electrical through PCBs. And if you notice with PCI Gen 5, you're starting to see a lot of cables because the signal integrity of the PCBs isn't good. So we're already migrating to cables, even at Gen 5, let alone Gen 6 and 7. And so if we're going to go towards cables, and then we're going to go towards optics with silicon photonics, a world of cabling on the electrical and signal thing it makes sense. So let's get much better management of the thermal of the water, and a bath of water just seems, whilst it sounds great, it doesn't seem great from a serviceability perspective and actually a water use perspective. This is a much more economical use of the water, and I'm not sure if you can actually recover 65C water out of an immersion approach. But I'm not saying immersion is not the way to go. I'm just saying this is an alternative that we're looking at here. This is very modular. these modules are all stepping repeat. So in terms of embodied carbon, we're fully embodied carbon in this. This is a very small module. Every module will have these same pieces ideally, and you just change the silicon. And you could reuse these module pieces when you scrap a piece of silicon and put a new module in. You just put a new PCB in and use all the mechanical infrastructure again. That's the sort of the premise. We're trying to design from sustainability first and starting from a clean sheet of paper. But using E3 modules and using these, in being inspired by the OAM module, the OCP accelerator module. So this is fundamentally based on the OCP accelerator module and E3.S, but packaging it from a sustainability energy efficiency perspective.
So may I ask again? I'm sorry. So the width of this module, it's like the width of the rack, right? Is that like 19 inch or 23
No,
inch?
this is 100. It's the size of an OAM module. We're talking, in fact, with Callum's feedback, we are talking about making this maybe slightly wider, maybe another 10 millimeters wider. So it might go from 102 millimeters or 4 inches to 112 millimeters, 110, 12 millimeters. And the module itself is 165 millimeters long or 6 inches, like the OAM, or including the cooling infrastructure, it's 200 millimeters wide.
200 millimeter. So it's not even 2 meter, right? It's 20 centimeter, correct?
Yeah, 20 centimeters. Yeah, it's tiny. It's tiny compared to a server.
Oh, okay.
It's the same size as an NVIDIA SXM, well, a bit bigger than an NVIDIA SXM module, if you know the NVIDIA modules.
Okay, I see. Sorry about this. I thought this was like a huge scale, a much larger scale, but it is not. Okay.
It's tiny. That's the whole idea. This is tiny. Okay, so, well, Callum, back to you, if that's okay. So we need to work out then a way. I think from a tolerance perspective, your biggest concern is this connection of the water between the top and bottom half. So we probably need a mechanical engineer on how would we do this and make it watertight and reliable. Is this fundamentally flawed? Or is there another way that we could attach these two parts? I guess is a question. Is that fair to say, Callum?
Yeah, I think so. I think a bit of mechanical analysis needs to happen for that joint.
Okay, all right. So that's a fundamental that we really need to get on top of sooner than later, if we can. Do you think there's anybody in your mechanical team, engineering team, that could look at, is this possible with the tolerance issues, etc., or not?
I think to do a deeper look at it, I'll have to go through our resource planning a bit, and I know it's a bit backlogged right now, but I can ask the question, Alan.
Okay.
I'll let you know.
And we do have some. I am establishing some work with Greg at IABRA. We're beginning to talk to some engineering that might be able to help us out, that he could basically fund. So I can bring this up as one of the key issues. So I guess in terms of issues, we've got this. So we've got the thermal management. So this was one we've highlighted for everybody that wasn't on previous calls. Can we actually thermally cool a 25 watt or 40 watt E3 module with this novel heat conductive approach? So we're thermally simulating that. I'd also like to build something that can where we can actually physically test this. But we've got simulations going on at the moment. Okay, so in terms of tolerance stack-ups elsewhere, Callum, the only other areas that I'm thinking of is, I guess, the spacing between these modules and their mating with these like connector type fingers for the thermal conduction as opposed to electrical conduction.
Yeah, and just to answer, I see Randy's question in the chat. There hasn't been a tolerance stack-up analysis, but that is definitely what we would recommend to do on any of these critical joints. But yeah, so Alan, the fingers themselves, the question would be tolerance stack-up for those because of depending on how they're connected to the main cold plate here to be able to conduct the heat. Because obviously when you have the card that needs to be where it is for the electrical connector, then you have to somehow make sure that the cold plate itself is in a spot that it will have appropriate contact to when it's cooling.
The mounting of the connector being so I worked for a company that made connectors, and we did mount multiple ones so I was introduced to tolerance stack-up issues there. I mean, relative to each other, I don't think it's too big of a problem, but on the basis they're going to be relative to this cooling plate, you've got a very good point. Now, what we did is we had jigs where you'd put all of the connectors into the jig and they would be reflowed onto the PCB together. So at least relative to each other, and they would also go into alignment holes in the PCB itself. So you would get a pretty good reflow in terms of the accuracy there, but there is obviously tolerance there. And to your point, the tolerance of that versus the tolerances inside the actual gaps here and the mating are going to be pretty important. I guess I allowed for about 0.5 millimeter of play in these connectors in terms of mating there, and you do have some sort of play in the actual electrical connectors themselves. I'm not sure what that is. Like obviously it's a similar makeup to what we see here.
Yeah, and so what you'd want to use to eat up the tolerance stack up between these finger cold plates, I'm calling them, I guess, and the E3, the peripheral, the media modules, you would want to use the thermal gap pad to eat that up. So that gap pad would be what's actually conducting the heat from the card to the cold plate. And so you have some compression on that gap pad and some, you look at a tolerance analysis as well and see worst case, do you have?
So I mean, these are spring-loaded pins, so these give you they're like a gap pad, but there's an air underneath them. So I was thinking that whether we can actually design these plates, and actually when we attach these plates, like they might be somehow physically mounted to the actual cold plate, and behind here, I was thinking that we could have some gap pad material. So as the module gets inserted, it compresses these and pushes up against the gap pad. So that's what I'm hoping we can get properly simulated. And I'm thinking that this could be a challenge to simulate accurately. And that's why I'd like to maybe build this as well to see if we can actually get a good thermal connection with this or not. And again,
you might get some inspiration from EMI gaskets there, which have solved similar problems.
Yeah, in fact, that's exactly it. Good point, Bijan. It looks very much like an EMI gasket, doesn't it? So, but yeah,
But I think you were referring to thermal interface, right, Alan?
That's the idea. It's not an it's space.
So an EMI is mechanical construct, with a known Young's modulus, whereas a TIM material or some sort of thermal interface material, the Young's modulus can vary dramatically as well, depending on the temperature of the environment itself.
Right. Okay. Yes. Yeah. Obviously, we are fundamentally. It's more. That's where I said we need to maybe put the gap pad between the spring and the copper plate that you actually this spring loading actually compresses the gap pad, and how effective would that be or not, as the case may be.
Yeah, so
companies can help us make these little assemblies.
And so where you'd also have the gap pad, Alan, is on the surface of that copper as well, connecting to the card.
Now that's a bit more challenging because this module is going to slide in from the top. then you would just tear up the gap pad, right? It's not like you slide it in and it compresses these copper these connector pins. So I can't see gap pad on the actual module itself. We'd have to have just a physical interface of these compressed.
How are you thinking that copper cold plate attaches to the card? Because you need to have the thermal connection.
Oh yes, no, actually between underneath this copper for sure. Yes.
Okay.
Good point. So you would have you would have a thermal grease giving you these I'm assuming are going to be like 15 watts of the 25 watts or whatever, right? And so and these are ones where you'd want to maybe, and they're probably slightly higher profile, that you would mate with grease or as efficient a gap pad or thin a gap pad as possible. Whereas these lower power devices, you just have gap pad, just like you see in the modules today. When we took a Micron CXL.mem modular apart at the MEMCon, Micron kindly did that. You know, we saw gap pad all over the place. So absolutely, in that sense, you're absolutely right, Callum. Sorry.
So were you thinking, Alan, that the cold plate would be mounted to the card itself? So when the card gets removed, it gets removed with the cold plate integrated?
Yeah, this cold plate would be part of the chassis of the card. So
okay,
yes, exactly. In fact, when I was talking to Micron, their CXL.mem is a double width module, and so Samsung's with air fins, because they do burn about 40 watts, which is you need double width for 40 watts. But we want to stay roughly in the single width, and so we did take the lid off, and sure enough, the components seem to be within the tolerances of a single width card. It's just it's double width because of the heatsink air cooled fins. So we would replace that with a copper lid, or maybe we can get away with aluminum, depending on the conductive requirements. And we just put that lid. So minimal modifications for the SSD and memory manufacturers is the idea. Or we could even modify them ourselves in an experimental sense.
Okay. So that definitely helps, because my tolerance concern was about between like that cold plate and the card itself. But if it's being mounted together, then you're good on that sense. Then yeah, you just worry about the tolerance of how it mates down at.
It's this mate, and it's this interface here is where the module touches these fingers of this connection is going to be a like whatever this is, some spring-loaded metal, which probably isn't as good a conduction as copper. The physical touch points are going to be fairly minimal to the copper plate, but behind this, hopefully the gap pad gets good connection from the connectors to the water flowing through this assembly. And so that's where the thermal modeling, I have no feeling it's 25 watts and 40 watts compared to 1,000 watts on the other side. So
yeah,
I'm hoping we can get away with it, but I don't know.
I know we're doing thermal sims, and that's good. I would be a bit concerned about this just because that is a pretty high heat load. I know it's a larger area, but yeah, that's usually within the regime of where you're wanting to have some sort of active flow close by or over top. But it is a larger area, so we might be okay. We'll see what the thermal sims say.
Right.
Because where I would also be concerned, Alan, is that connection point, depending on what that spring-loaded thing looks like. If it's something like this, where you actually have less surface area at the joint, like there's those gaps, you want like as much contact area as possible. So yeah, I would just be a bit concerned about whether we can conduct all the way down to where we need.
And so just on that, we've got that front plate, and we also have these little sidewall ones as well. So the water would be flowing down these walls and up the other side, as well as going through along here. So we'd have the opportunity here, and again, we could raise this higher. And actually, in fact, I did have a wedge lock design for those of you that are relatively new, all the way to the top, and we were looking at a wedge, like the military wedge lock approach. but I was wondering if this might be a little bit more, this gives us more flexibility between modules. And so, but yeah, so potentially we could grow height here if we wanted more thermal contact up the module. But yeah, lots of, this is where I think a sim and like I say, actually building the real thing is probably, if we can, so I've got a small model of just one module in one with water going in and over this assembly area. So we could actually probably quite cheaply build this and quickly test it for real, because I'm a bit scared that thermal simulation won't be that representative of reality. With this setup.
So are there water coming to the top of the module? How do you like evenly have the heat distributed in the entire module?
So the water comes in here, the blue is cold, so we've got 2 inlets at this end and we've got 2 outlets at this end. It comes directly into these modules first and it flows down all of these veins. So if I just get rid of all the modules.
So the whole module, like when you open it, right? There's no pipe inside those modules though, right? So they're just water all over the place.
These little modules don't have any, at this stage in the design, don't have any water in them. They're all conductively cooled down to this plate here. And the water is flowing in this plate and through these copper veins, which we'll come on to another one of Callum's points, is they're flowing through these copper veins here. So you've got water nearby the interconnect. And this will be at the coldest inlet water temperature. The way we've got it currently designed, I don't have a design of the input of the flows to show you, but the water will initially flow down all the way through these 2 modules to the other side, on both sides from both inlets. It will then return and then return down the middle modules and then come down to here. And then it will, we don't show the interface, this is what we were discussing earlier, then it would transfer to the top coolant area and flow across the 1 kilowatt GPU, CPU switch, whatever, and then it would come out of these hot ones. So and then it would be at 65C if the flow is controlled coming out off of the big processor. So the modules relative, because they get the cold water first, they're getting the lowest temperature and have the highest ability for the differential between the water temperature and the device temperatures. So that's, and then when we come to the main kilowatt device, we've got some ideas which we've talked about in other meetings of different techniques to try that. Okay,
so inside those modules, I'm sorry,
no
sorry. Inside those modules, as you showed earlier, are those memory chips, right? And then the 2 big ones at the bottom. What kind of chips are they?
So that was just an example. That was the open memory interface module. When we were looking at an IBM Power 10 module that has 2 OMI memory channels in that module. But if you take a CXL.mem from Samsung, you have a controller sat down near the bottom, and then you have the memory chips in a similar fashion, or an SSD. You have a controller chip near the fingers again, and all the flash memory up and down the module. So it's that sort of type of layout is what you typically see, and the controllers typically burn a big chunk of the, like 50% or so of the total power of the module, and the rest of the power goes to the media, which is distributed through the many chips.
I see. Thank you.
And Michael, I presume I described that well enough. Samsung.
Sure, yeah.
Okay, so all right, so I think the key points here then, Callum, so far at least, is we need some mechanical work going on in terms of the attachment of the top and the bottom water chambers. and is that actually possible with the tolerances? And assembly at assembly time rather than a sort of a you can't take the damn thing apart. So I think that's, in fact, then mechanically, how do we bolt these things together as well? It just crossed my mind, so that you have a good seal. And overall, I guess we said a first order tolerance stack up analysis is what we were saying, and the other one was this thermal interface, which is what we're trying to model already, right? But we were talking about the mechanical stack up there between the connector mount, because the connector mounting are going to be toleranced. They're going to move around a little, and relative to this is just how much do we have, and does the compression piece of the thermal attach soak up the tolerances enough or not? Did I explain that very well, Callum?
Yeah, I think that's what it comes down to, is making sure that there's enough play in that mechanical thermal joint to allow the electrical connection within its tolerances as well.
Right. Okay.
Yeah, I was gonna say, Al, do you want me to just quickly go through some of these? Yeah, so some of these now you can actually disregard. For example, this third bullet point about forces from the gap pads flexing the cold plate fingers. Now that I understand that cold plate is mounted to the card first, that's less of a concern. But still,
well, actually, I read that differently, Callum. So, I read that you were concerned that the thickness of this copper piece here, which is extremely thin at the moment, which is why we're going to widen the module, when you plug the module in, it'll be pressing against, although it'll be pressing against the entire face here, all the way down, would the pressure actually bend this thin piece of copper? Would you actually push the module, bend it over because of the compression of the connector would actually bend these? Because these are only, at the moment, this is only 0.6 millimeters thick, and I'm thinking that that's too thin, and I need to make that 1.6 millimeters thick. I need to add a millimeter between each module, so that's why I make the module wider. I guess that wasn't your concern.
No, but that's a valid point too. So what are those? What's the intent of this copper finger sticking up there versus just having the cold plate from the modules come down to the surface without those?
Okay, so let me just, that's a good point, just so you can see what I mean here. Let me turn these back on. Did I turn back on? No. There we go. Okay, so what I've done is I've oh, wow, there it is. Right, you see this module. So this module, the lid, you can see that the lid actually extends down into the connector space. So this will be a slight design extension to the lid that you replace on a traditional SSD. So it sort of extends down like the fingers of the connector, right? And it's mating here. So this is one piece of copper that's part of the disk drive or the SSD or the CXL.mem, etc. And it slides and mates here. So this is all fixed. And obviously it compresses this. This needs to be a separate spring, like a traditional connector pin. This is made separately and has to be attached to the actual water, the back plate here, this water cooled back plate. But but underneath here, you can see that actually there's a wider, this is where the water runs through. This is a copper below here where the water actually runs through. And this will be the finger that comes up that we make these thermal connectors to. So does that make sense? Have I answered your question? I'm not sure I've answered your question.
Yeah, so I think ideally you try to eliminate if you can eliminate fingers coming from either, like try to make it so it's only coming from one side. So that skinny part coming down from the cold plate of the module goes down all the way as far as it needs to without needing that the copper that's in between the gold kind of connector right now. It would be good to eliminate that and just have that come from the cold plate on the module itself. Does that?
Oh, so we turn this into like a double-sided spring-loaded one single piece. Oh, that's interesting.
I'm just thinking from a manufacturing perspective, like if you can avoid having that skinny feature needed on that lower half and just have it on the upper half, that would be beneficial.
You mean this skinny piece here?
Yeah. It really comes down to thermals, I guess, but
yeah, I was thinking that this is all part of this assembly. So I'm hoping to make this an extra millimeter wider, so 0.6 becomes 1.6 if I do this.
were you thinking of flow within that 1.6?
No, there'll be no flow, but this will be part of the this will be part of the solid block that this gets made out of. However we make it, the water will actually flow below it here. That's in this area here. This is a fatter piece. You see, this is 4.5 millimeters, which would be 5.5. So the water would actually flow in the fatter piece below, but it would all be part of the same mold, or whatever you want to call this copper block. So so you have a good copper connection, good thermal connection down to where the water is flowing. That was a reason for this.
Okay. Yeah, that makes sense, Alan, because the only way you could do what I'm saying is if the connector itself has a good conductivity as well, and you'd rely on that to connect the copper on the main block here to the cold plate above.
Yeah, I was trying to get as much area as possible to bolt this, and that was the reason for putting gap pad behind this spring-loaded connector here, so you get a good thermal mate from this to the copper, which is then attached to where the water is flowing directly underneath this. So, and likewise, in the walls, the water is literally flowing directly up and down the walls, right behind these.
Hey, Ellen.
Yep.
This is Randy. So I'm looking at those metal fenders, which are there for thermal purposes. And what are you saying that thermal interface material is?
The connector, this gold thing.
Because I'm looking at the thermal path, and you would have to have, if there's some sort of thermal material, you would have to make sure or ensure that you got sufficient compressive forces, or you're not going to get phonon transfer, so you're not going to get heat movement through there.
Right. So that's the reason for the thermal modeling. Yeah. I'm no thermal expert, so
because it's only at the high compression points, if you will.
Yes.
Will you most likely have low thermal resistance?
Right.
So
right.
in a sense, the top and the bottom of that. And then
Yeah, so
the
just
concern becomes there could be a thermal resonance that could actually influence the overall operation.
Oh, really?
Yes.
Never heard of
Those
that.
gaps, for example, between those fingers, the spacing, that could create an undesirable opportunity thermomechanically.
Right. So the gaps here. Oh, these gaps. You're saying that this actual
the lateral. Yes.
That gap. Okay. I mean, look. In fact, this design is like this to make it look like the EMC shields we've seen.
Mm-hmm.
Why are the EMCs not one big solid plate? I'm assuming for some compression regions. But very good point.
Yeah, it has to do with insertion force, but remember, any gap becomes an antenna. So any straight edge, if you will, becomes an antenna, or this area becomes an aperture, and it can start to radiate electrically. But mechanically, thermomechanically, you can have resonances.
Wow. Okay. Yeah, you learn something every day. Thank you. All right. So, well, the design of this then is, you know, in the size of this gap may be important if that's the case, for sure. Yeah, so I guess so. So Randy, you'll know from your experience the wedge lock approach up to delivery systems. Are you familiar with the wedge locks?
Yes.
Yeah. So that, I mean, we started with that approach. We could go back to that approach, but I was favoring this for if it works for various reasons. So
Yeah,
okay.
some first order analysis, some CFD or thermal analysis. We can take a relatively quick look at that.
Okay, well, that'd be great. All right, so I think we've done that one pretty extensively then. So we know this is a big area, right? So I think I've made the decision just in the last couple of weeks that I definitely need, we want to thicken these modules by about 1 millimeter spacing each, and maybe add a couple more around this area as well. So I'm looking to extend the module width to 112 from 102. But to be honest, I looked at this. I'm going to have to start the model from scratch, which is probably a healthy thing to do. But it might be the right time as well for a mechanical engineer to get involved, because this is more I'm an electrical engineer, and you know, I have fun with these mechanical ones, but I'm not a mechanical engineer, so that will be good.
Hey,
where we
Alan, when you're talking about adding in that 1 millimeter at the bottom, will that increase the gap between the modules?
Yes, effectively you will. Well, so the module thickness, the industry standard for the EDSFF is that these modules are 7.5 millimeters wide,
Right.
and the gap is 9.3 millimeters. That's in the spec.
Right.
But we've made them 8 millimeters wide for a couple of reasons, because the chips inside sometimes are that there was some flaws in EDSFF when it was designed. Let's just put it that way. You can see the flaws in the design. But so the 1 millimeter, the extra millimeter, will give us a little bit more thermal mass on this copper lid for conducting the heat down. But we didn't extend the gap. We kept it at 9.3 millimeters because we're not blowing air through this. We thought we could do that. But as I built this thermal structure up, I realized that we were just being left with a hair's breadth of copper here. And so, as well as extending the width of the module to 8 millimeters, from 8.5 from 7.5 millimeters, I think we need to increase the spacing from 9.3 millimeters to 10.3 millimeters, if that answers your question.
Yes. Okay. Thank you.
But at the moment, it's 9.3. It is fully compliant with EDSFF right now, but but I was going to extend it to 10.3.
So you have the lids made of copper. How about the cold plate in the back? What material are they made of?
The body here.
Yeah.
Yeah, this will be the body that the SSD or memory manufacturer uses, which is typically, from what I've seen so far, it's a cast piece of aluminum, or a routed piece of aluminum, and they gap pad to this as well. So this is one solid body with the hole cut out for the PCB and components. So this would remain the same as to whatever the SSD manufacturer has used, which I believe is an aluminum body.
So the lid is actually a cold plate that is considered the copper lid is the cold plate, or
Yeah,
where is
and so is the aluminum. The aluminum body is a cold plate, and there is a thermal mate between the lid and that cold plate itself, right? So the whole thing is, and this lid doesn't need to be copper necessarily. It could be an aluminum lid, but that will depend on our thermal analysis as well.
I see. Thank you.
At the moment, I'm assuming it's a copper lid, but not necessarily.
Alan, I need to drop off now, but one thing I wanted to quickly mention just on the wall of compute side is I know you've been mentioning like treated water and things like that. So I want to check, were you picturing just facility water going through these versus a secondary fluid network?
So there's two networks, right? I don't want to turn this one, it'd take too long to load, but so we've got a column of modules, 16 modules.
Yeah.
And so the water pipes are going down and going through each of the 16 modules. So you have a cold feed and a hot return. That's pumped, and there's a heat exchanger at the top. So that's one closed loop in a vertical chain, and then the infrastructure water goes to all the heat exchangers.
Okay, that's good. Yeah, I wanted to make sure that it's a separate secondary closed loop.
Yeah, that would be the idea. Yeah.
Okay. Yeah, I have to drop off, Alan, so I can go through some of this in more detail.
So we didn't really get through many of your questions. So, maybe we can continue with a bit of an email discussion around your other points. Might not be a bad idea, but anyway, what we did cover today was good. So thanks, everybody.
Thanks for being patient with my questions.
No, that's fine. And
Yeah,
like,
thank you on that.
Yeah, no, as people join, maybe if you'd like, guys, there's this wall of the HPCM wall structure. I can go through, or there are some videos that you could watch as well. But I could either do a separate hour with people if you're interested, and you can ask all the detailed questions to get your head around what we're doing. But I do have some on. There is some slides on what I presented to Oak Ridge National Labs recently, and I did do a recording of what I presented to the composable memory systems sub-project, which is on YouTube. So and I posted those on the wiki, so you can see those videos as well if you want to get a bit of a bootstrap on where we're at.
Okay, so what date is that the posting, the recording? What date? Because
yeah, let me just bring this in here for those of you interested. So
all right, guys, I had to jump off, but thank you, Alan, and I will definitely take a look at those videos.
Yeah, so it's on the OCP HPC wiki, and you'll see that on June, it's a very top one at the moment. CMS Tech Summit, CXL enablement presentation. That's the slides, and there's a recording of it. It's a 15-minute recording. It'll give you a quick, a very quick. It'll probably get you a load of questions, but that will be a quick bootstrap. And also the slides I shared with Oak Ridge National Labs are there, a couple below as well, on comparing it to Frontier, etc.
So on the June 13 or June?
So June 13 is the Oak Ridge National Labs. You can see the slides I presented to them, but the June 28th is what I gave a couple of weeks ago to this Composable Memory Systems Tech Summit. And there's a recording there.
Okay, great.
So just type in Google, just do OCP HPC wiki, and you'll come to this page.
Right. I know how to get there, yeah. Is it on YouTube as well, or not on YouTube?
Yes, on YouTube. The recording takes you to my YouTube channel.
Okay, great, thank you.
And you'll see a bunch of other stuff from me in there. All right, guys. Well, thank you very much for joining. We'll speak to you in a couple of weeks.
Yeah, thank you very much, Alan. Yeah.
Thank you, Alan. Bye-bye.
Bye-bye.
Hey, Randy, this is the first time you've managed to join us, right?